Welcome back. It's time for another worked example. This time we're going to treat a rolling wheel with friction again, same one we did last time, but this time we're going to use angular momentum. Let's remind ourselves how this works. A wheel is thrown horizontally with a speed of v0 at a time t equals 0, with the surface of the wheel just touching the ground at the point of release. The initial angular velocity of the wheel, omega 0, is 0 radians per second. The coefficient of kinetic friction between the surface of the wheel and the ground is mu sub k. And just like last time, at first the speed of the center of mass of the wheel diminishes while the angular velocity increases. The question is, what's the final speed of the wheel after it stops sliding? That's the question. Let's look at the demo again just to remind ourselves how that works. So here's a 3D demo of a disk, and it's on a kind of a track here. And I'm graphing down here two things. The v is the velocity of the center of mass. This guy's going to start out with about 3 meters per second of velocity. And omega times r, which is the speed of a point on the rim of the disk relative to the center of mass, that's going to start at 0. The idea is somebody throws the thing, it's not spinning at all, but there's friction between the point of contact and the ground, and so the thing slowly spins up to speed. At some point it reaches the velocity where the speed of a point on the rim is equal to the speed of the center of mass relative to the ground, and then the point of contact stops slipping. So let's see how that works. You can see that the speed is dropping, the angular velocity is increasing. At some point they reach equality here, and that's where the thing stops sliding. Starts at 3 meters per second. It looks like it's ending up at around 2 meters a second. There you can see it, 2 meters a second. Let's see if that makes any sense. Okay, so we've got the same system, we've got the same diagram. We only have a slightly different question, which is what's the final speed? Notice the question did not ask how long does it take for the thing to slide without slipping. It only asks what is the final speed. So this represents an opportunity for us to analyze the problem differently. Last time we calculated the angular momentum and the torques about the center of mass of the disk. This time, let's see what happens if we choose the initial point of contact as the origin of our coordinate system about which we compute angular momentum and torque. Okay, so we have the same angular momentum principle. The rate of change of the angular momentum is equal to the net torque. We still have the same three forces, so we have to compute the torque produced by those three forces again. Now, the normal force acts straight up, right? But about the point of contact, it actually produces 0 torque. The Earth pulls down, but again, about the point of contact, it produces 0 torque. But what about the normal, or the frictional force? Last time, it did produce a torque because it was a distance r away from the origin, away from the point about which we were computing torques. But this time, notice that it acts at the point of contact, and so it also produces no torque. So all three of these forces produce 0 torque. In fact, the only one who could produce a net torque would be the frictional force, because the normal force and the weight, as we learned last time, actually add up to 0 net force, so they can produce no net torque in any case. The key is that frictional force. Because we're picking the initial point of contact as the origin, that guy produces no torque. So we have the sum of the torques is 0. That means the rate of change of the angular momentum is 0. That means the angular momentum is actually constant in this case. How can that be? Let's look at the angular momentum. The angular momentum comes from two pieces. It's the angular momentum of the center of mass relative to the origin, plus the angular momentum of the material in the disk orbiting around the center of mass, or spinning around the center of mass. You can think of the first term as the translational angular momentum, and the second term is the relative angular momentum of the parts of the disk about the center of mass. Let's see how that works. First of all, let's calculate the translational angular momentum. It's the distance between the origin to the center of mass, r, crossed into the momentum of the center of mass. So that's going to be m times the velocity of the center of mass is the momentum, and the distance is r, and the cross product is going to point into the page. So it's going to have a negative z component. What about the rotational or the relative angular momentum? Well, that's just I times omega. I, in this case, is the inertia of a disk, 1/2 mr squared. Omega points into the page, and therefore the multiplication of these guys, the scalar times the vector, has a negative z component. Both of these guys have a negative z component. If the rate of change of the angular momentum is 0, it means that the sum of these two guys at the beginning has to equal the sum of these two guys at the end. Right? The angular momentum has to be constant. Now at t equals 0, omega is equal to 0. So that means the rotational part of the angular momentum is going to be 0. But the velocity of the center of mass is v0. So if you put that in, you get that the total angular momentum at the beginning is mv0 times r. If you do the same thing at the end, you get the translational part is mv final times r, but you get that the rotational part is I omega final. If those guys are equal, it means the guy at the beginning, mv0 r, must be equal to the angular momentum at the end. Now I can substitute for omega and I, and you'll notice that a bunch of things cancel. First of all, we've got an m in every term, we've got an r in every term, and so those guys all cancel out, and I end up with a very simple result, that the initial velocity is 1.5 times the final velocity. And of course you can solve that for the final velocity. So this problem turned into basically a 2 or 3 liner using the concept that the angular momentum had to be constant because the net torque about that particular point had to be 0. Very nice.